Too many overtones, John.
You need to speak in a different frequency.
Okay, I think we're ready. I'm going to be patching some examples of this idea as I go. And basically, are you recording now? Should I start? Should I not? Okay. I'm Jon Sonnenberg. Some of you might know me, some of you might not. I've been speaking here. I think this is my 5th year speaking here, and I often speak on different topics. And this is another topic that you're here for. Welcome. We're talking about wave replacement synthesis today, and many of you don't know what that is. I've been involved in electronic music since '84, so over 30 years now, I guess, if I do the math right. And this is a term that I coined in 2012. So if you haven't heard of it, it's because you don't read my blog. And if you want to read my blog, I do have a lot of information on there, different topics that I talk about, and it's artoftravelog.com. My band is also Travelog, and I've been playing music for most of my life, like most of you. I'm not going to get into what a patch is. I think that's too basic for this room. I'm not going to get into what a synthesizer does. I think you guys know what a synthesizer does. What I am going to talk about is the concept of replacement synthesis and replacement modulation. Greg, have a seat on the floor.
Yeah, I'm going to do that. Gotta get my oscilloscope.
Nice. So we all know different types of synthesis, right? We talk about, what are some types? Additive, subtractive. I talked about additive a couple years ago. Phase distortion. Yeah, and different companies have come out with these different methods over the years, but all of these different methods, all of these different ways to synthesize a sound have been around. I mean, you could do it on the first Smokes, right? You can frequency modulate another waveform. You can phase modulate another waveform. You can do subtractive synth, which we're all familiar with. And usually when we approach a synth, we think East Coast or West Coast. I think most of us do, and we have an oscillator into a filter into a VCA, and that's where we all start. This is a totally different idea in synthesis that doesn't really rely on, it is changing a harmonic spectrum, but we're looking at the time domain rather than the frequency domain. And if you think about it in terms of that, basically what we're going to do is we're going to take a wave shape and we're going to replace sections of that waveform with other waves. And to do this, it's very simple. You don't even need a filter. All you need is a couple oscillators. And so right now, I have, this is probably way too small to see, unfortunately. But if some of you want a better look at this, maybe make the waveforms a little larger. I have the composite, if you will, of these wave shapes on this oscilloscope here. So whatever I'm doing, you can see here. Now, somebody tell me what happens when you get a ramp wave or a negative sawtooth wave and you sum it with a positive sawtooth wave. What happens when you just add it together? Yeah, right? They sum together and they equal 0. It's just a straight line. In this scenario, however, what we're going to do is we're going to take a control voltage and we're going to just simply take that voltage. Let me get enough cables. There's several examples that I'll go through and we'll see what we get to in all of these. examples. Let me change these. So I'm using 3 VCAs. One is an output VCA, just so I can have control here that you can hear. Okay. One of the VCAs is just used for the modulation source because these particular amplifiers have a nice positive and negative output, and I'm using those to modulate the here. Let me patch it in, get it working, and then I'll explain what's happening. That might be a better. So what I'm doing is I'm using a pulse width modulated source out of the same oscillator. And maybe what I should do, let me rearrange something here. Since this is too small to see right now,
That's pretty loud.
is it pretty loud? I'll turn it down just a bit. Just a minute. I'm going to use channel 2. Maybe we'll be able to see that a little better, see what I'm doing. I lost the tracking. Let's see. Oh, that's why. I know why. Because I had the pulse width all the way to one side. What happens is it's not triggering on that. So let's change some of these waveforms so you can see them next to each other. What we're doing is we're actually controlling. I have this signal. It's coming out positive and negative, controlling 2 different VCAs. And then depending on where this pulse width is, you're getting 2 different waveforms. So the idea is you're replacing part of the waveform with another segment of another waveform. Okay? Now, there's a couple different things we can do here. And one thing that I really think is important is, first of all,
Can you turn it down?
yes, let's try this. Hold on. Let me plug this in again, and I'll get to where. Is that better? Can you still hear it okay? Okay. So one thing that's interesting about analog synthesizers is the resolution. This can be done on wavetable synthesizers pretty easily, but the resolution on an analog synthesizer to change voltages is an electron. So you can get a lot tighter resolution, and the voltage control is always smoother because of that. So one thing I want to do is I'm going to show you one way, and I was going to patch everything up ahead of time, but then I thought that would be too.
You have this patch on your blog now?
I don't have this patch on my blog, but but if you email me, I'd be happy to tell you exactly what I'm doing here. So if you're confused about some of the things I'm doing, or if you want more information about it, that would be fine. Here's something that I think is kind of important for the next patch. Let's see if I can get this. So I need to get the output of this. Now see, since I'm running different channels here, I'm going to swap these out for a second. I think it would be a lot easier if this scope was bigger, but it's not, so I'll just work with what I have. So this is a hard synced sine wave. We're familiar with hard sync, and basically what happens is it's resetting at a certain point. But what's not obvious is, and this goes back to knowing your equipment, knowing what oscillators you have. One point that I want to make is you might have an oscillator that has multiple waveform outputs, right? You might have a sawtooth wave, you might have a square wave. It's all generated from one core. So there might be a triangle core, there might be a sawtooth wave core, but all the sine waves and everything that you see are all generated from that same waveform. So you can use external modules to get pulse width waves that instead of starting from one point and spread this way, they start from the end of the waveform and spread this way. That's important because when you're syncing up waveforms, some oscillators work on the trailing edge, some work on the leading edge. In this case, I have it, so now, because I'm syncing this waveform, even though they're in phase with each other, can everybody see that? So the pulse width is actually controlling the phase. Now the second thing I'm going to do is take the pulse. What? Okay, so going back to, let's see. If I take, I'm going to rearrange some cables for a second, and here, this might explain it better. Okay? With this scenario, I'm controlling the pulse width of this top pulse, right? Now, the oscillator that's generating that, this is where a multiple scope would come in handy. What's happening is because this is the leading edge, what happens is the period of the first oscillator is really right here. And see if I can, I need a 4-channel scope. Hey, I have one. I need it to be brighter. I need it to be big. I'm trying to think of a good way to show the phase relation between these two, because really what happens is the result. You see it here, right? What's happening is this sync point, because we're changing the way that relates to the waveform, we're actually getting a phase difference.
And what are you modulating there? That's the pulse width on that oscillator?
So I have a pulse width, yeah, like a PWM.
Yeah.
And because I inverted the PWM, so the trailing edge is in the middle, that's the point at which the waveform starts. So if it's synced, and you can actually get harmonic ratios, and then you can change the phase of that too. Does that make sense more? Does everybody understand that? Any questions before I go on? Okay. The second part of this that I'm going to show is instead of a sine wave, I'm going to take a pulse wave out. Okay? What this is going to do is now I can control the pulse width and its position in relationship to the fundamental. And in doing that, if I use this signal to switch, and let's go back to the noisy sound source here. I'm going back to the other two waveforms, if you will. And now that I have the amplitude down, it looks like I need to up the amplitude a little bit. So right now we're hearing here's a sine wave switched on one channel. The other channel, I don't have anything in yet, but let's take a sawtooth wave, okay? And now let's do two different things. Let's take a sawtooth wave out of our fundamental. So think of this as you have an oscillator, and now we're going to be switching in a portion of another waveform. And this portion of the other waveform, we can vary the pulse width. Let's trigger on the first channel so it's a little more stable, okay? We can vary the pulse width. So all on one side, we have a sawtooth wave now. On the other side, we have the sine. And in between, we have something else. It's not a blending of the sound. It's not a mixing that you would with volume control. It's actually, it's in mathematics, we talk about piecewise functions. You know, if there's any mathematicians out there, and you have periodic functions and you have piecewise, where like every so many radians you're getting a repeating pattern, but it's actually this segment is repeating. Okay, is that loud enough? To me, it sounds a little low. Maybe just a. Say again. That's better? Right there is good? Okay. So again, because we're changing phase as well, one thing that's pretty interesting about this, see, maybe I should go up in frequency. One thing that's interesting is we can also control the position of where this is happening. Let me do one thing here. I'm going to take, I want to see if I can get this triggered better. So I'm just going to take one of the outputs of this waveform here, so it's not rotating around all over the place. And maybe I can... No, that won't do it. Okay, I'm not going to do that. I'm just gonna go with this and then show some of the ramifications of this, okay? So right now, notice as we're changing this window, part of the waveform is this sawtooth wave, part of this is the sine wave. All we have to do to switch these, we can easily just switch the two waveforms into the inputs of the two amplifiers, and then the waveforms are reversed, where one side is, now the other side is the ramp, the other, you know. So side A before was the sine, side B before was the sawtooth. Now I switch those two waveforms, and now you have something a little different. Now, one of the cool things about this is you can cause, we like things that change. We like pulse width modulation. We like oscillators beating against each other. We like filter sweeping sounds. We like things that are not static, right? Even vowel sounds, like our language. We talk about diphthongs, where we say a word like pi. Our language is very complex. It's not the same vowel sound through the whole movement. It's actually something that's changing. Now, one couple things that are really interesting about this method of synthesis is ultimately what we're wanting to create is a waveform, right? And this is a direct look at the waveform, whereas you can you can do a lot of interesting things by replacement of the waveform into different things, and then you can modulate it. So even if you want this to not be a static sound, like if you want an LFO, for instance, to modulate the width, it's as simple as so everything is control voltage ready. And the resolution, like I said, is very good. So I'm going to show a couple examples of this, and I think you'll get the hint. So what happens is sometimes when your pulse width goes all the way to 100% or 0%, you start getting things that aren't quite syncing up, and you get some interesting jitters and stuff. It's almost more interesting than digital synthesis to me, just because you can cascade stages of this as well, and you can it's unlimited as far as how many stages you can cascade, and you can actually have segments of the waveform, depending on the number of oscillators and filters and stuff you have. So something I want to also point out see, that's really nice. Something I also want to point out, let me get these back. Filters are typically low pass, high pass, band pass, and they're made to take out frequencies, right? Now, something that's kind of interesting with this, and I'm just going to simplify this patch. Let me take out a lot of these cables, and let's just go back to a simple waveform. And this time I'm going to do something slightly different. Instead of using a bunch of VCAs to do this, because what I was doing is I was taking a square wave through a control voltage, using it as a control voltage over 2 VCAs, and one of them was inverted, so you get one waveform when you don't hear the other, and then when it's flipped, you get the other waveform.
I'm trying to grasp how you're combining the two signals. You say you say you're not mixing, you got one oscillator and sync another?
So the idea of sync is they're starting at the same point, right?
But that's how you're patching it. You're patching one oscillator and syncing with another?
I'm using, yes, I am. Yes.
Are you using the pulse width modulated signal to sync the other oscillator?
I am.
That's okay.
I am. Exactly. Does that make sense to everyone?
So you have one oscillator that's a sine wave, another oscillator that is like a saw wave or something.
That's what I was doing in this example, yes.
And what we're using is to sync
Both of them.
As long as it's the same.
So the only reason I'm syncing them is so they're in phase, so when you switch one waveform to the next,
so they're saying
yeah, you can use the same you can use different waveform outputs from the same oscillator and to get the same effect. The only reason I wanted to switch it and sync it up is because then I also, so let's think of it this way. If you sync up a waveform and you're pulse width modulating that, let's say this is the waveform that you're syncing to, and you have a pulse width here, and it's synced to the rising edge, let's say. That synced waveform is shifting back and forth in phase, in a different phase angle with the first oscillator. And then I'm taking the pulse width output of the synced waveform, and that pulse width is voltage controllable too. That's how I was getting this window that could be anywhere in the waveform, and it could be any width. Does that make sense? Okay, back to filtering. This is something that I find interesting. Now, I wrote about this around 2012, but I've been experimenting with this ever since I realized that the best The best companion module with any oscillator is a fader. And it does the same thing that we just talked about. The fader can fade between two different waveforms, right? And if you use a square wave into it, it's going to switch it. So originally when I started doing these patches, I was using a fader. And let's say we have, again, a sawtooth and a ramp, and our output will just be here. And what did we lose? Did we lose audio? Oh, I know why. It's there, but we don't have audio because I need to patch it into the output, which I must have removed when I was pulling all of these cables. Just a minute. It is right here. Okay. This is using the fader module, and if we use this fader module, okay? Oh, one thing I need to do. If we use this fader module and we're switching between, what are we switching between? A ramp and the inversion of the ramp. So again, if you combine them in equal amounts, you get nothing, right? But instead of combining them like that, we're going to switch them hard from one side to the other. And this is wave replacement.
And this is the same, you're using the switch. the same
This is,
oscillator.
yeah, right now I'm not syncing anything. I'm just using this different outputs from the same oscillator into the fader, yeah.
Is this the same principle behind the audio WTF? Is that a different thing? WTF oscillators are basically play that into a module.
I do not know.
Okay, because that's, they call it window transfer function, which is where, yeah, you're using the pulse width to kind of combine waveforms.
I know that the new Paula Maddox module.
Right, yes, that's what.
Oh, okay. Okay, the difference with that is it's a wavetable, and it's always in the center of the waveform, and you're opening the window this way. In this scenario, you can take the wavetable and switch it anywhere, and it's all continuous.
I see.
So it's a little different. Now, yeah. Now something I'm going to do is I'm going to take instead of what I'm doing here, let's see if I can get this to really show. Instead of two different waveforms, now I have the same waveform going into a multi-mode filter. And I have the high pass and the low pass output, okay? And I'm switching between them. So this has a lot more ramifications than just simple wave shaping. You can actually have frequency-dependent wave shaping. And so if you go one side, that's one side, the other side is high pass. And then if you go in between and you're switching between the two, and again, this pulse width is going to change your window of where that is. And you can easily cascade these, like I said, and have different windows in different places. So something else I will say about this is if they are not in phase, if you don't have your oscillators perfectly synced up, something really interesting happens. For instance, if they're tuned just ever so slightly differently, that window is shifting along and it's beating, so you can switch between two. Let's go back to the two triangle waves so it's a little more obvious. what's happening is now this window's shifting. So sometimes you might get a perfect, if this is 50%, sometimes you might get something that's more or less a perfect triangle wave. Okay, the other thing that I think is really interesting, and I don't think we'll be able to see it so much here because I need more channels on the scope. You'll see the resultant wave, but let's see if I can get it with what I have. Okay. Here is an example. And what I'm doing here is it looks like a triangle wave, right? And it's a triangle wave on one side. So it's a triangle wave on one side, it's a ramp on the other side. But one thing that's interesting is you can start playing around with the frequency and you can shape the slope of that descending part of the triangle wave, okay? And this is of course voltage controllable too. So ultimately, if you can think of segments, and obviously if we limit that, you just get a little bit So what's happening here is if we listen to one waveform, okay, that's just a triangle there. The other side, it's synced, but it's a sawtooth wave, so it's always starting at the same point. If we don't sync those, let's see. If we don't have these synced, what happens is it just starts getting chaotic. And depending on where this second waveform is, it can just get a little messier. So hard syncing is one of the reasons to keep everything nice and neat. And then when you're syncing in different parts of the waveform, they're all lined up. Any other questions right now? I am, but with a square wave. So the square wave is actually, yes. So the square wave is all on or all off. It's all one waveform or all the other waveform. There's no crossfading happening here, yeah.
And so I know if I try that in the digital domain, I'm gonna get a lot of clicks to the top. Why are we not hearing?
Because it's
Something
because
there like this 10 or something, but you know, when there's a disconnect,
why does it sound so nice? Is that your question? Okay, well, let's think about a wave shape, right? A wave shape. I'll tell you exactly why that's happening. A wave shape, if you think about a wave shape, right? What happens at higher frequencies compared to lower frequencies? It's bigger or smaller. And what does that mean, actually? It's tighter. A wave shape, what we're hearing through the air, okay? The speakers are transducers that change electricity. We're seeing a voltage change here. The speakers are making the air pressure change. And what happens is if you see a waveform, right, and you put a discontinuity in it, right, a very steep slope, what's happening is the air pressure changes a lot faster. That creates higher frequency content. So discontinuity is higher frequencies. Something really smooth and continuous is lower frequencies. Okay? In the digital domain, we have what's called the Nyquist frequency, right? The highest sampling rate, right, that you want without getting aliasing. So if you're making a discontinuity in the digital domain, you're creating a lot more higher frequencies, right? And you have a great, the power spectral density of the waveform, it's a lot higher in the higher frequencies. And what happens is you're going above the Nyquist frequency, so you hear a lot more pops. In this situation, there is no sample rate, this is just pure analog waveforms, you're switching in and out, and when you create high frequency content, it sounds really pleasing, right?
You're switching it with a VCA.
Right now I'm using this fader, which is basically 2 VCAs, and that's what I patched up to begin with. 2 VCAs, I was taking a pulse output and inverting it. With a fader, I can just take the pulse directly, and it's just pushing it back and forth. What frequency am I switching at? The frequency that I'm switching at right here is in the same period, right? So I'm using the pulse width from the same oscillator. So if you have a ramp and a saw or something and you're trying to switch between them, you're switching at the same point every time at the same cycle. That's one of the reasons it sounds like it does. Now, let's go back to, this is all the same oscillator. And instead of, let's take a synced, hold on. Okay, let me make sure that we're synced up properly. Just a minute. How are we doing on time?
You've got
Okay. I'm sure I do. Oh.
I don't know when these are supposed to end. I assume an hour and a half is what the lectures are running.
I think we're given like an hour. Well, there's
1:45.
there's 2 rooms and they're switching back and forth. So if I go over 20 minutes, it means if somebody wanted to see the next lecture, they either have to leave early or they're stuck here 20 minutes and they're 20 minutes late. So, but I mean,
You're still doing better than Mike Clark.
that was a great lecture, by the way. Was anybody here for that?
Which one was that?
It was like Synthesis 101. But basically, he played a bunch of the hits and explained how he got those sounds. So it was pretty cool. Something I wanted to show. So right now, we're back to, your question was how fast are we switching, right? If we're synced up and we start, let me see if I can, hold on. Let me do this a different way, because what I want to do is I'm going to show the switching wave again on top, because I think that will clear up a little bit. Or maybe the switching wave on the bottom rather, right? Okay, that was close. And then,
Hey, John, is a pulse width that's doing the switching, is it on the sinking or the sunk oscillator?
right now it's on the sunk oscillator.
The sum.
The synced oscillator, right? Right. Before, this is on the, right now it's on the master oscillator, okay? And I switched it to the synced oscillator, but what I want to do really quick,
I was gonna say, drop the frequency of the sync oscillator. Yeah. Make it sunk.
But see, it's also what we're hearing too. So we also have the two waveforms going into the fader. Let me make sure that they're still going into the fader. Let's go back to, so we have a triangle, and let's take a, okay. And obviously we lost this signal because now we aren't on this cable. So it was a lot easier using a 4-channel scope, and I'm sorry that this screen is so small, but it is a lot brighter and you can see it better. Okay? So right now, if we take out the pulse width modulation, right, we have a saw and we can blend. This is the mixing. This is using the fader as just a mixer. We're fading between a triangle wave and the sawtooth wave, right? And what I'm talking about here is not fading at all. It's actually a hard switching. And so when we switch them back and forth rapidly, now we have something completely different. Now the other thing is, if we take that switching pulse out of another synced oscillator and it's at a higher frequency, it's switching many times in the period. Okay? You can change that frequency because it's synced and it's still in phase. You can also change the pulse width. And again, you can cascade this into another switcher and have even more segments of other waveforms come in. So you can, this is a piecewise synthesis of a waveform. You aren't talking about subtracting the harmonics out or adding more sine waves. This is actually looking at the shape. And in some ways, I think it's more intuitive. Sometimes we get caught up in what does the waveform look like? This is actually, like, you can do some really interesting modulations, like of the slope of the triangle that I was showing. Okay? Any other questions? Yeah.
Like a high frequency capable sequential switch be used in place of a crossfader or VCA?
Yes, it can. Now, in fact, I have a suit and tie guy's switch here, and it works. There's a couple caveats to that. And let's say, I'll show you an example. Let's take 2 of these waveforms. In some ways, it's nice because this particular switch, I have a ModCan modular system too, the ModCan B series at my house. That has a voltage-controlled switch that does this a little differently, better in some ways, worse in others. The problem with the switch is there is a sampler in here. And there's here, I'll just show you. Let's say,
You mean a sample at all?
there's a microprocessor that's switching the levels here. Let's hold on 1 second. Let me do this, and I'll show you exactly what I mean. Let's take the output of the switch. And why is my amplitude not very loud? Oh, because I turned it down. That would help. Okay, this is a voltage-controlled switch that works on 0 to 5 volts. And part of the problem is you do have to offset the waveform so it's up in that range, because most of these oscillators are swinging -5 to +5. Okay, so you have to limit it and you have to DC offset to have it in the range. The other thing about this particular switch is you have it so even after you offset it, that 5-volt range goes between 4 different inputs. So it's switching between, so you could have 4 different waveforms switching in different periods of that waveform just by having a ramp each section, kind of like a wavetable oscillator when you're sweeping between, you have voltage control over the wavetable and you're sweeping between the different waveforms. It's similar to that. So it's good in that sense, but there's a little more to it. And there's a little more level shifting and getting it just right. There is something, however, that this switch does that I really do like. See if I can. Also, did you notice how the amplitude just went way up? The reason is you have a sawtooth wave, right? And we were looking at such a little window of that, because the voltage-controlled switch here, even though it's 0 to 5 volts for 4 different inputs, we were -5 to +5. So we were looking at a very small window of voltage there. And so you have a sawtooth wave, a ramp wave, and you're looking at a little segment, and the amplitude of that segment was really soft. It was not very high in volume, so it wasn't very loud. Now what I'm doing is I'm actually going to go to the switch. This switch is interesting because you can actually take let's see if I can just raise the frequency and get this resolution a little better. Triggering on this is not my friend right now. What we're seeing now, what's happening, and this is where this switch comes in really good, really handy. This, in my opinion, this is no longer waveform replacement. This is chaining. You're taking one waveform and then you're chaining a whole other period of another waveform. The Casio CZ101, Casio CZ series, did this exact thing where you could just take a couple different waveforms, chain them together. Then it did phase modulation, which is, it's pretty much just a single case of frequency modulation where you take the same oscillator and you modulate itself. And you have the shift in the period that way. So I think, yes, you can use a voltage controlled switch. Yes, you can use a switch for other periodic changes. One thing that's nice about this particular one, let's see if I can get the triggering to be a little, trigger level is, see if I can get this to, I would like it to be, I would like everything to be magic and always work. Can anybody help me with that? Good idea. There, perfect. One thing that's cool about this particular switch is you have the first 2 outputs. The first 3 outputs, right now there's nothing, there's a gap here, so it's just not happening. Or you can have 4 outputs, right? And it's just sequentially stepping through those. One other thing I want to mention, LFOs can now be heard. Just the rising and falling of a voltage now in low frequency, way below. Do you see what's happening? So a portion of the waveform now, and before when pulse width was only moving this way, now you can have a segment of a pulse width wave shape where it's almost a staircase and you're rising that stair segment up and down with an LFO. You could cascade a bunch of these and have different segments do this as well. So it's just another tool that might help you get more creative with sounds when you're making sounds. You know, I think, again, sometimes we're stuck in the idea of subtractive or additive or wave shaping. You know, we're stuck in these constraints that the synthesizer is this open-ended, amazing tool that we all have, most of us have access to. And I think this is just another tool that you can use. You could have a segment that's completely random. You could have one portion of your waveform completely random, either in level, or it can be the frequency of maybe that sawtooth wave that you're mixing in. You can also instead of using an LFO, you can also use another ramp. And now here's where like beating really comes into play. Like you can really see so it's kind of like an LFO, but you're taking that segment, and because it's not in phase and it's shifting, you get something kind of moving. You get a lot more movement with this type of synthesis, yeah.
Is there any chance your blog could address some of these patches that you're talking about today?
Yeah,
Yeah, because that'd be nice to actually go and look at the way you have it patched.
sure.
Yeah.
So that's the idea behind replacement synthesis. One last thought. I did have one just trivia question when we were talking about different modes of synthesis. Does anybody know what vowel consonant synthesis is and what piece of equipment it came from?
Well, the last module I'm aware of that most people use is the BOSUN, which was developed at the Institute of Sonology. But it basically looks at the form and peaks of, it's basically the result of doing acoustic analysis of speech. So the idea is here, so the vocal system is basically, and so your vocal cords buzz and its frequency, and then that configuration is filtered. The resonant peaks of that are used for synthesis.
I love your guess, and I'll give you a consolation prize. The Casio home keyboard actually used something called vowel consonant synthesis. I better do this. Wake up, back row. Yeah.
Because the STG switch is a four-way sort of window comparator switch thing, were you using a ramp or a sawtooth instead of
I was using a ramp instead of a pulse. I do have the tags, if anybody wants one to stick on there. And also, who got the prize? What's your name? What is your name? Gregory. Here, let me.
Is it a puppy?
No. It's this is what I released
No, it's okay.
in 1990.
The radio program.
What do you play it on?
Sunday night. It'll be on there.
That is called a cassette. And that's the first release I ever did. www.artoftravelog.com.